Welcome back, guys. This is the unit that we have been working for the entire year. This is, if we're climbing a mountain, this is like the summit of the mountain. All the work we've done, all the different units, they all come together in this unit on stoichiometry. Even though we're going to get to the summit on this of our mountain, remember, we still got to make it back down the mountain. So there is still stuff to be done. But this unit on stoichiometry puts everything that we've been talking about all year together and wraps it all up. If we look at what we've already learned that goes into stoichiometry, we talk about atoms and ions in this. We look at, have to use the periodic table. We have to be able to write and name formulas. We have to be able to balance chemical equations. We need knowledge of moles, percent composition. We need to know types of reactions so we can write our chemical reactions. We need to do factor labeling so that we can do the math in this. We also need metric and talking about the elements. There's a lot of stuff in here that we have done all year long that have building up this. This is kind of like our apex, our climax topic right now. We're still going to do a bunch of stuff after this, but it's kind of less dependent on what we've done before. So that you'll find out why we've been so particular about making sure you know everything in this unit. So let's go ahead and get started. Stoichiometry is the study of the quantitative or measurable relationships. So quantitative, we mean numbers, relationships that exist in chemical reactions. Okay, if you give a chemical equation, if we give you one quantity in there, maybe we give you grams of the first substance, you should be able to determine how much we should be able to get out of any other substance in that equation. Okay, and the way that is it relates through moles and through our coefficients. So there's going to be a lot of math, a lot of factor labeling in this. So if you're struggling with factor labeling, make sure you come in and see me. So let's first go back and talk about balanced chemical equations. Okay, we take this one here. Nitrogen gas plus hydrogen gas gives us ammonia. If we can interpret this that we have one particle of N2, 3 particles of hydrogen gives us 2 particles of ammonia. Or if we look at these coefficients in terms of mole, we'll see that 1 mole of N2 gives us 2 H2s, which then converts to 3 moles of ammonia. Or finally, we can look at this as mass. 28 grams of N2 plus 6.06 grams of H2 gives us 34.08 grams of ammonia. That's kind of, all these are obeying the law of conservation of mass. And because of this, the idea that matter is not created or destroyed, it's just changed forms, allows us to do these stoic problems. Okay, so let's use this equation up here to answer this question. If we react 5 moles of N2, how many moles of H2 will we need? Well, we know the ratio of N2 to H2 is 1 to 3. So if we have 5 moles of N2, we must have 3 times more moles of H2. So what's 3 times more than 5? 15 moles of H2. Pretty simple. Let's try another one. If we're reacting 0.25 moles of N2, how many moles of NH3 can get? Well, it's a 1 to 2 ratio. Okay, so if we have 0.25 moles of this, we must have twice as many moles of the NH3. Well, that's going to be 0.5. Now these numbers are pretty easy. The problem comes in with what if we have 2.76 moles of N2, or some numbers that we can't easily figure out in our head. This is when stoichiometry comes in and we start setting up our problems. But the first thing that you must do with stoichiometry is you must determine the molar ratios. What's that mean? You must balance the equation. If you don't have a balanced equation, stoichiometry doesn't work. Okay? Because we take advantage of those coefficients in the ratio between different atoms or different molecules to make this work. So you must balance your equation. What do you must you do before you balance the equation? Write the correct equation. If you don't have the correct one, you're not going to be able to balance it. Okay, guys, what you see here is basically the blueprint for solving stoichiometry problems. What I want you to do is to copy this chart down, pause the video, copy it down, and when you are done copying, hit play and I will explain this to you. Okay, the chart's basically broken up in 2 sides, the known side and the unknown. this is what how you're going to flow through these problems. You're known as what you're given in a problem. Generally, you're given one of three things: either your grams of a substance, the moles of a substance, or the volume. Notice we want to get to moles. Well, in our molarity unit, we learned that going from grams to moles, well, that's our atomic weight. Our formula weight gets us there. Going from volume to moles, that came from Avogadro, where he told us that 22.4 liters is equal to 1 mole. So once we have moles, we can then convert from moles of one substance to moles of another using the coefficients from the balanced equations. And then from there, if they want it in grams or volume, we can separate that. So make sure you have this copied down. You're going to need to know this. Okay, this kind of shows you how to flow. I don't think I'll ever have you recreate this, but if you don't know how this looks and how to flow through here, you're not going to be able to do these problems. Okay, so first part of solving factor label or stoichiometry problems is you must factor label. Okay, there's no can I do it this way, this. No, you must use our factor labeling. Okay, we need to see how one substance changes to another. With that, when you factor label, you must include the formula. So 12 grams NH3, 12 grams CO2, whatever. You must include the substance because we're going to switch from one substance to another, and we must see where they end up canceling each other out. And as always, remember, round all atomic weights and answers to 2 decimal places. Okay, here is our first sample problem. Determine the mass of calcium oxide produced by decomposition of 50 grams of calcium carbonate. Okay, first thing you need to do is be able to write the equation. Well, it's a decomposition of calcium carbonate. That's one of those special ones, metal carbonate. So what's that break down to? Well, it's a metal oxide plus carbon dioxide. So let's write the equation. Okay, there's our base equation. If we look, we have one carbon here, one calcium here, one calcium here, one carbon, 3 oxygens, 1, 2, 3. So this is a balanced chemical equation. So we're good here. So we got the balanced chemical equation. Okay. Once you have your balanced equation, you're going to set up your factor labeling. You're going to look at that flow chart and find out where we're starting and follow the steps through that flow chart. Well, in this problem, they gave us, I believe, 50 grams. Okay. So remember, in a factor label, you must write the formula for the substances. Okay. So we must write what chemical or what compound we're talking about after the numerical value. Okay. So it's adding one step to our no naked numbers. So we started with 50 grams calcium carbonate. That's going to be in the upper left of your flowchart. First thing we need to do then is to convert grams to moles. Okay, so we use the periodic table to find the formula weight of calcium carbonate. Well, 1 mole of calcium carbonate is equal to 100.09 grams of calcium carbonate. So what we see now is we set it up so our grams of calcium carbonate have canceled out and we're left with moles. Our next step then is to go from the moles of known to the moles of unknown. And the way we do that is to use the coefficients from the equation. So if we look at our equation, we know that 1 mole calcium carbonate is equal to 1 mole of calcium oxide. Remember, if there's no coefficients put in front of a compound, we assume it's 1. So now our moles of calcium carbonate have canceled out. We're left with moles of calcium oxide. And the last thing they wanted to know it, I believe, in grams. So we have to convert from moles of calcium oxide to grams of calcium oxide. We use that doing our formula weight. So 1 mole of calcium oxide is 56.80 grams of calcium oxide. Once again, moles cancel out. We're left with grams of calcium oxide. Okay. Now we need to do the math. So I would take my calculator, 50 times 1 times 1 times 56.08 equals, then divided by 1 equals, divided by 100.09 equals, divided by 1 divided by 1 equals, and you should get an answer somewhere here of 28.01 grams. So we're starting with our known. We're converting from grams of known to moles of known. And in this step, we convert from the moles of the known to moles of unknown. That's what we're trying to figure out, our unknown. And finally, moles of unknown to grams of unknown. So make sure you're following this. Look at the flow chart. Follow. Let's go ahead and try another problem here. How many grams of potassium chlorate must be decomposed to yield 30 grams of oxygen? Once again, this is a decomposition of a metal. Okay, it's one of those special ones. Remember, the metal chlorate will break down to metal chloride and oxygen. Okay, so here it is. I went ahead and balanced it for you already. So we are starting, our known is oxygen. Okay, we're starting over here. It doesn't matter if you start with information of products or reactants. Okay, it works the same. So set up your factor labeling table. Start with what you know. I have 30 grams of oxygen. So that's the first thing I'm going to do. Now I have to go, that's my known, so I have to go from grams of known to moles of known. Well, I know that 32 grams of oxygen 16, right? 2 of them is 32, is equal to 1 mole. Now I'm going from moles of O2, I want to go to potassium chloride. So I know for every 3 moles of O2, I have 2 moles of potassium chloride. So I want to get rid of oxygen, so that's going to go on the bottom. So moles of O2 now cancel out, and then I have 2 moles of KClO3 on the top. Now it wants to know grams, so the final thing I have to do is get rid of moles of potassium chloride to go to grams, and I can use my periodic table to figure out the formula weight. Okay, so I have 1 mole of potassium chloride is equal to 122.55 grams. Okay, so once again, I'm left with doing the math. So 30 times 1 times 2 times 122.55 equals, then I'm going to divide it by 32, divide it by 3 again, and I should end up with 76.59 grams. And I should actually write KClO3, so potassium chloride, after that. So that's a complete answer. Are you getting the hang of this? I hope so. Okay, try this. Assuming STP, remember standard temperature and pressure, how many liters of oxygen are needed to produce 19.8 liters of SO3 according to the following equation? Now, for this problem, you don't have to remember what STP is at 0 degrees Celsius and 1 atmosphere. What that just lets us know is that the gas is at normal situation. Okay, so we're starting with 19.8 liters of SO3, and we want to find how many oxygens we need to react. It needs to react with SO2 to produce it. So once again, set up your factor labeling. Okay, 19.8 liters of SO3 is what we start with. Well, liters to moles, we know that 22.4 liters is equal to 1 mole. My liters cancel out. Now I have moles of SO3, and I need to go to moles of SO2. Look up here. For every 2 moles of SO3, I have 1 mole of O2. So there's my ratio. 1 mole of O2 for 2 moles of SO3. Now I've canceled out my moles of SO3. I'm left with moles of O2, and they want to know liters. Well, once again, I know that 1 mole of any gas is equal to 22.4 liters. Now all I have to do is my math. So 19.8 times 1 times 1 times 22.4 equals, then divide that by 22.4 equals, then divide it by 2, and when I do that, I should get an answer of 9.9 liters of O2. Okay, hopefully you're getting the idea of this. Use that flow chart to move through the steps. Generally, we're not going to see anything bigger than a 4-step problem. 1, 2, 3, 4. So you should be able to follow this. All right, I want you to try this problem on your own. So pause the video here, copy it. When you are having part 1 and 2 done, come back and hit play, and we'll see how you did. Okay, question number 1 said, if 7 moles of octane are burned, how many moles of water will be formed? Well, here is the combustion of methane, right? Anytime we combust an alkane, we get carbon dioxide, and water is a byproduct. So start with what you know. I have 7 moles of octane. There's octane. Okay, and I want to go to water. Well, and I want moles of water. So this is just a conversion from one substance to another. So if I look at my ratio, I know that for every 2 moles of octane, there's 18 moles of water. So I'm going to have 18 moles of water on top, because that's what I want to end up with. 2 moles of octane on the bottom, cancel, cancel. I'm left with an answer of moles of water. I take 7 times 18 divided by 2, and I get 63 moles of water. Hopefully you got this same answer as well. Okay, second part says if 10 moles of O2 are used, how many grams of CO2? So we're starting with moles of O2. We want to go to grams of CO2. So we start with what we're given, 10 moles of O2. Now my next step is to get it to the moles of unknown. Well, I know my ratio is that for every 25 moles of oxygen, there are 16 grams of carbon dioxide. What I want to get rid of goes on the bottom. What I want to keep goes on top. So 16 moles of CO2 over 25 moles of O2. Now I just need to convert 2 grams of CO2. I use my periodic table, and I find that 1 mole of CO2 is equal to 44.01 grams of carbon dioxide. Once again, do your math. You should have got an answer of 281.66 grams carbon dioxide. All right, I want to do 2 more practice problems here with you. Okay, once again, copy this down, and then once you get your answer, hit play and check yourself. So how many grams of aluminum chloride are formed when 50 grams of aluminum chlorate are decomposed? So you may need to dig back in your note to check on the decomposition of aluminum chloride. So pause it, answer it, check your answer. All right, so here is our formula. Remember, metal chlorides break down to metal chlorides and oxygen. Remember, +3 -1 crisscross. That's how we get that formula. Same here. This is a -1. This is a -1 +3. So don't forget the parentheses. Very important. So let's start with what we know. 50 grams of aluminum chloride. Now we got to go from grams of known to moles of known. So 1 mole of aluminum chloride is 277.33. This is where rounding becomes really important. If you don't round correctly, as I've taught you all year, this number is going to be off and you're going to throw your answer off. Okay. Now we have moles of known going to moles of unknown. They want to know aluminum chloride. So it's a 2-to-2 ratio. So 2 moles of ACl3 to 2 moles of AClO3. Okay. Yes, you do need to write this. Even though these cancel out, what we're doing is we're switching from one substance to another. So you do need to write that steps. Then finally we need to go from moles of AlCl3 to grams of it. And we do that this way. Okay. Run these numbers through your calculator and you should get an answer of 24.04 grams. Okay, one last problem. If 100 grams of water is decomposed, how many liters of oxygen will be formed? So you're going to have to go back and really think about this one, because we talked about water breaking down as a compound. It's breaking down to 2 simpler ones, so 2 simpler must be hydrogen gas and oxygen gas. Remember Brinkelhoff's. So pause it, come back to me when you're done. There's our equation, water breaking down to hydrogen gas and oxygen gas. We said we could do this by putting a little electricity through it. It's kind of cool when you see this because we can actually burn that hydrogen gas off. It's a pretty cool experiment. Okay, so start with what we know. We know we have 100 grams of water. We got to go from grams of water to moles of water, 18.02 grams per 1 mole. Now from water, we need to go to oxygen. It's 1 mole of oxygen per 2 moles of water, 1-to-2 ratio there. And then finally, it wants to know liters. Okay, so we know that 1 mole of oxygen is equal to 22.4 liters. Okay, so 1 mole goes on the bottom, 22.4 liters goes on top. I take 100 times 1 times 1 times 22.4 equals on my calculator, divided by 18.02 equals, divided by 2 equals. And that gives me an answer of 62.15 liters of oxygen. Now remember, with your answers, if you don't have your units and you don't have your substance, it's going to be wrong. Okay, guys. Hopefully you were able to follow this. We are going to spend some time doing practice problems in this. The key to doing this is, first of all, to know that flowchart. If you know the flowchart, you should do well. Second thing you need to be able to do is write those balanced equations, but in order to write balanced equations, you have to be able to write the correct chemical formula. So revisit bonding. And finally, you're also going to need to know reaction types. So make sure you know those. If you don't, you need to do a lot of revision. Go back and watch some of the old videos. Come in and see me for help. If you're not understanding this, come in before class and see me so you can get a head start on everybody else. Like I said, this is the summit of our mountain that we've been climbing all year. Okay, we want to get you here. You've been working hard. We want you to understand this. So make sure you ask questions. Okay, and we will be doing more stuff after this, but it's more independent things that aren't as heavy related on everything we've done all year. So until next time, guys, take care, and I will talk to you soon. See ya.